unit, we learned about rate laws and how to determine information about the rates in which reactions proceed. Well, now in 5.4, we're going to start talking about how the mechanism actually works. So most chemical reactions occur by a series of steps called a reaction mechanism. To understand this, we have to know what its mechanism is. So one of the main purposes for studying kinetics is to learn as much as possible about the steps involved. The balanced equation for a reaction tells us the reactants, the products, and the stoichiometry, but it does not give us any direct information about the reaction mechanism. Remember, when we were first learning about rate laws, you cannot infer that a coefficient is the order of the rate law. So, for example, this reaction between nitrogen dioxide and carbon monoxide produces nitrogen monoxide and carbon dioxide. The rate law for this reaction, it shows that it is a second order reaction. Oops, go back, please. So second order, because it has the 2 right there. Okay, but then these series of steps are proposed for how the reaction actually proceeds, where the reds are oxygen and the blue is nitrogen, so that would be NO2, and this would be NO2. So in step 1, we have 2 nitrogen dioxide molecules collide with each other to make, this would be nitrogen trioxide and nitrogen monoxide, which is one of the products that we need. Okay, then the step 2 has the NO3 that we don't need in the equation react with the carbon monoxide, which was the other reactant, and that forms some more NO2 and then the carbon dioxide. Okay, so this is a proposed mechanism where the 2 products are formed in 2 different steps. They're not formed in the same step. And so we would have to really study this in order to see if this would be a correct mechanism, but it is a proposed mechanism for this. So these series of steps, we have intermediates, which are, in this case, it would be the NO3, where it's a species that's not a reactant or a product that's formed from the final equation, but it is consumed and formed during the reaction sequence. So if we were to add the 2 together, then the NO3 would cancel away. Okay, so anything that cancels, that would be called your intermediate. The 2 reactions themselves are each called elementary steps, and that can be written from its molecularity. And we're going to talk about molecularity a little bit later, but that has to do with how many reactants are involved in your rate law and your reaction. So we have 2 requirements for a series of steps to be accurate for a chemical reaction. First of all, the sum of the elementary steps must give the overall reaction. So if they're on it's just like when you're finding the ionic equation, opposites cancel out, same sides add together. And then the second requirement is that the mechanism must agree with experimentally determined rate law. So it has to match what the rate law was experimentally figured out. So this is going to be difficult to do. It's going to be a learning curve process. But in order to meet the second requirement, the overall reaction can be no faster than the slowest or rate determining step in the sequence. And we're going to go in further about rate determining a little bit later. But how do you figure this out? How do you figure out what the mechanism for the reaction is? Well, the rate law is always determined first. Usually that's given to you. And then using chemical intuition, which is just maybe like some reasoning in your brain, that's what that means, and following the 2 rules previously mentioned, the chemist will construct possible mechanisms and tries to eliminate the least likely and leaves the most likely. Now, even though it's most likely, doesn't mean it has to be. So we just have to be careful with that. Okay, so let's see how this works. For the balanced equation of nitrogen dioxide reacting with fluorine gas, we get the NO2F. And the rate law is determined experimentally to be as follows, where the NO2 and the F2 are both first order. The suggested mechanism for this reaction is shown. Is this an acceptable mechanism? Meaning, does it satisfy the 2 requirements? Well, let's work with it. Okay, so the first requirement is that it needs to balance. When we add them together, the first requirement, it needs to add to the balanced equation. Okay, so I'm going to change my color back to red. So when we add these two together, ooh, that's a highlighter. Let's go red pen. It's not red. When we add these two together, we are going to just condense them down into the same equation, canceling what we can and adding what we are not able to cancel out. So the only thing that I see that can cancel is the F's of lone fluorines, and nothing else cancels. So the two NO2s will add together. So 2NO2 plus F2 makes, and then these will add together, so we'll have 2NO2F. So does that equation match the balanced equation that it's supposed to, which is right here? And it does. So that means that it meets the first requirement. Check that one off your list. So that we're on our way. It does match that first requirement, that it adds to the balanced equation. Okay, now the second requirement was that it has to match the experimentally determined rate law. So the second requirement, match rate law. Okay, our rate law that was determined is already listed for us because somebody else figured it out, is right here, where the rate is equal to the NO2 times the F2, and they're both first order. Well, because in our overall equation we have two reactants, and both reactants are included in the rate law, and even though we have a 2 on the NO2, that doesn't tell us that that has to be the order. That could mean that it does match the rate law, and this could be a possible mechanism. So after you go through both of these points, when you prove the first one is really easy to prove, that when you add the two together, they should equal what it should be. That one's easy. The second one, making sure it matches the rate law, is a little bit more difficult. And you just have to look at, okay, I have two reactants in my overall equation, there are two reactants in my rate law, so that could be a possible mechanism. That is going to be a little bit more difficult to understand, wrap your head around. So in total, this does, yes, this could be the proposed mechanism. But then, like, if we were on the AP exam, you would have to go into further detail in explaining why it matches the balanced equation when you add them together, and then it matches the rate law because it has two reactants and the rate law has two reactants. Okay, we'll talk more about this in class.